Welcome to the London Mackerel, where we discuss finance and other stuff. Today I want to talk about an interesting theorem, a rather esoteric theorem about geometric averages and arithmetic averages. It might be an esoteric theorem, but it will unfortunately affect our portfolios in this time of COVID. Of course, we're in a very unfortunate time now where COVID is hitting, sadly, not only our health, but is also hitting our wealth. And this innocent-looking theorem implies that we might be, or some of us might be, even poorer. So before I go on, let me just do the obligatory legal stuff. Please bear with me. I will do this very, very quickly. No advice is being given or solicitation being made. This is a purely educational video. You must consult your own professional advisors. This is a short video to describe complex ideas that may be simplified. When you simplify complex ideas, there's of course a loss of information. And I'm not responsible for any errors. I'm sure that there are some. Okay, so this theorem was first proved by a man called Augustin Louis Cauchy. Hopefully we can get his Wikipedia page up very, very quickly. There we go. And Cauchy was a very famous mathematician who worked in the beginning of the 19th century. If you studied pure maths at university, you almost certainly would have come across at least a few of his theorems, notably his mean value theorem in analysis. You might have also seen his integral theorem. He started life in the most practical of professions, an engineer, but graduated to pure mathematics. And the little theorem I'm going to talk about, I think he proved in a book he wrote called The Theory of Analysis. And it's sometimes called the Cauchy mean theorem. And we can look for the Cauchy mean theorem. And when we look for the Cauchy mean theorem, we see a lot on the mean value theorem, but which is very, very different to the mean theorem. We see very, very little on Cauchy's mean theorem. So it's relatively obscure. But what does it say and what does it mean? What does it mean for us? Oops, So to jump right in, I'll write it out, and I'll write out. There'll be a little bit of maths, but don't worry, we're going to get to hard and relevant examples very, very soon. So again, please bear with me on this. We look at an arithmetic mean or an arithmetic average. I've just written AM for arithmetic mean there. And that is the sum. You might recall from high school that sigma is the sum of a whole lot of results. Xi, I might run from 1. You might have n of them. And you look at the average. So you divide through by n. And this is an arithmetic average. It should be familiar to you. And his theorem says, or the mean theorem says, that is greater than the geometric average. And the geometric average is the nth root of these observations, x1 times x2 times all the way up to xn. And because I'm a pedant and I can't help myself, I'll say that is the same as this little three-sided rectangle, which means you multiply all the xi's together. And because we're taking the nth root, you raise it to the power of 1 over n is the same as taking the nth root. And the left-hand side of the inequality is an arithmetic mean or arithmetic average, and the right-hand side is a geometric mean or geometric average. And there's this technical point that because we're taking nth roots, we need all the xi's to be greater than or equal to 0. So let's just look at a practical example of this, and we can jump into what it means. Supposing, over the course of a year, you do some course, and over the course, you write 3 tests out of 5. The first one you get 3 out of 5. The second you get 4 out of 5. And then you get 5 out of 5, and your mark is an average of those. Well, you don't need Excel to work out the average, but I'll use it anyway. Hopefully everyone can see it's 4. And the average of your test is 4. Now that's the arithmetic average. Well, we could also work out the geometric average, and we see that the sum of all of those is clearly 60, but I'll do it anyway because I'm going to just play with them very briefly. So the product of all of those three numbers is 60. And so the geometric average is the cube root. We've got three numbers, so we take the cube root. And the geometric average is 3.91. The arithmetic average is 4. And as the theorem tells us, the arithmetic average is greater than the geometric average. And of course, if you got the same mark in the test, so you got 3s the whole way around, then obviously your arithmetic average is 3, but also your geometric average, well, that's 3 cubed effectively, and you're taking the cube root of 3 cubed, so obviously that's 3. So then they're equal. But you would ask, well, many people use arithmetic averages. In fact, we use them all the time. We very rarely use geometric averages, and people would say, well, why do we even think about geometric averages? And where geometric averages are very, very important, of course, are in finance. So imagine that you're investing, let's say 100. In your first year, you earn 8. And in your second year, you earn 4%. So these are your returns. And straight away, you can see that your arithmetic or your arithmetic average return is 6%. But when you work out how much money you've got after 2 years, let's make this year 1 and year 2. So we see it's 1.08 times 1.04. And after 2 years, if it's times by 100, if you've invested 100, you've got 112.32, and your return is 12.32% over 2 years. But when you want to work out what your return is each year, because effectively you're multiplying these factors together, you're multiplying the 1.08 and the 1.04 together. On top there, you would take the square root. You would take the square root of that factor for 2 years to work out what your annual return is. Raised to the power of a half, which is the same as saying the square root. And lo and behold, our return for 2 years is 5.98%. There it is. And that is a geometric average. Now you might say, well, the difference between 5.9% and the 6% arithmetic average, that's really very, very small beer. And why are we getting all het up about it? But when you're in times of extraordinary volatility, and unfortunately we are in times of extraordinary volatility, this effect becomes very, very marked. So, if you look at the S&P 500 now, for example, the major US index, its high, I don't think this was its exact high, but its high was about 3360 in February. It was that was its approximate high. Okay, it fell down over the last couple of weeks. It's been as low as 2280 about. That's its approximate low, and we all hope that is as low as it will go. And it's now, and this is over Easter 2020, so it's now at about 2800. I think it's just a little less than 2800. So let's say now. And if we look at the returns, what those returns mean, that means that from its low, from its highs to its lows, it fell 32%, nearly a third. And even from its highs to where it is now, whoops, sorry. It's fallen nearly 17%. So we've seen extraordinary volatility, and in fact, I think that before the Easter weekend, the session on Thursday, it went up about 1.5%, if memory serves. And, people hardly noticed that, whereas a few months ago, 1.5% would be seen as a big move. And indeed, when there'd been moves of 2 or 3% in a day, moves that a few months ago would have been headlines in the financial press, people slightly shrugged their shoulders and said, well, yesterday it rose or fell 6 or 7% or even more. So that's hardly worth mentioning. And the point really that I'm making is we have seen fantastic volatility. And I know a few people who've said, look, their portfolio is down. minus 30%. Their savings portfolios, they've lost 30% on their portfolios. But they say things like, well, not really to worry because it'll come back, next year. That's their view. They say, well, next year, I'll make back 30%. So I'll be fine. I'll be square, right? And really what they're saying is that the average between minus 30 and plus 30 is 0, so it'll be a wash. But even if that happens, and of course it's a huge if, a huge if, but even if that happens, let's look at the effect on their portfolio. So if they started with 100, their 100 went to 70, so there's a factor of 0.7. Okay, and then they might make back 30 in the next year. That's 0.91. In other words, their 100 would have turned into 91. And they've lost 9% over 2 years, okay, instead of breaking even. And in fact, if we work out their annualized return on that 91, we can do a little geometric average again. We see that it's minus 1. We see that it's minus 0.46% about. And my point really is, and the point of making this video is that not many people who invest really know and appreciate this fact, okay? And we can ask what's happening here. And just to illustrate this to you, you might say, well, what happens, would it make any difference if instead of the markets falling and then going up, the markets went up and then fell? And because the technical term is multiplication is commutative, it doesn't make a difference. And the effect that you're seeing is exactly this, is that let's say you start at 100 and in a good year you go to 130. So that's your good year. But now when the markets fall in your bad year, you lose, you've got a larger amount in the market to lose. So that factor of 0.7 applies to the 130 and you're at 91. And even if we reverse the order and we say, okay, if the bad year comes first, I mean, again, this is very simple mathematics, but to get an intuition for it, the bad year comes first, we're down at 70. And now when the good year comes, and you're making 30%, you've only got 70 left in the market instead of the 100 you started with. So again, you're back at 91. So, if you have a good year first, then your big amount gets hit by the bad year. And if you have a bad year first, then when the market recovers, it recovers on a smaller amount. And to illustrate what this can mean over a lifetime of investing, I baked up a little example a few minutes ago. And I've said, okay, well, we've got two individuals, Ms. Stable and Mr. Variable, and they get the same arithmetic return over a 2-year period. Ms. Stable is fortunate. She gets a rock-solid 3% over 30 years. 3% is not that great, so maybe she's not terribly fortunate. But she gets the stable return over 30 years. Mr. Variable, he understands compound interest as well, and he wants a nice compound return, but he's in a far riskier portfolio, and he makes 15% in 1 year and loses 9% in the second year. So after 2 years, he's up 15 minus 9, he's up 6%. Like Ms. Stable as an average. But what happens at the end of the 30 years? And Mr. Variable might say, well, on average, I've got the same return as Ms. Stable, so I really should make as much as her. But that's the same arithmetic return. And if we take a look at it, we can see that the total sum that Ms. Stable has is, let's say she's invested 100, so she's got 1.03 to the power of 30, and her return is obviously that minus 100. So she made 142. Mr. Variable invested 100. For 15 years, he earned 15%. So that's 1.15 to the 15. And for 15 years, he lost 9%. So that's 0.91 to the 15. And so he's only got 197. And his return, he's only made 97. And if you look at it, you look at the difference, if you look at what the effect is, you can see that he's made about 68.5% of what Ms. Stable has earned. My writing is terrible, sorry. So he, over a lifetime, even though he's got the same arithmetic return as her, because his returns have been more variable, he's made nearly a third less. And this is the little lesson from this theorem, is that it's a relatively simple theorem. The proof is not that hard to follow. I won't go through it, because while the proof is not that hard to follow, it's by no means trivial. But it's still a relatively simple theorem. It's fairly easy to understand and to see in practice. But it has big implications, and it has big implications particularly when times are volatile. And if you're a passive investor, these are the people who really get hit by this kind of volatility. And volatility hits passive investors in all sorts of ways. Very often it persuades them to sell when they shouldn't sell, or persuades them to buy when they shouldn't buy. It also makes their portfolio returns seem far worse because their portfolios aren't rebalanced. Whereas an index, for example, is often rebalanced, and this effect is just often more apparent when markets are very volatile or after a great deal of volatility. So volatility does hit passive investors, and now here is another effect where passive investors really are hit by the fact that even though they might earn the same arithmetic return as someone else, if that other person's returns are far more stable, at the end of an extended investment period, they will have far less. Well, they'll have significantly less. And if over this 30-year period there's a few crises, and if you think about it, we've had crises now, crises in 2009, in 2007, in 2001. If you have a few crises, then this effect can become even larger than I have shown here. So it says if you're a passive investor, by all means, if your financial advisor recommends it, invest in equities and in investments that get you high returns and that might have some volatility to them. But as far as possible, within those constraints, try and earn stable returns. That's far easier said than done, of course, but I just thought I'd make you aware of this, or at least show you this neat little theorem, which is an esoteric theorem, but that has really sadly practical consequences for us. And on maybe that less than cheery note, I will thank you very much for listening to me and say goodbye.